Well, my name is Herbert Owen. I work at the Barcelona Supercomputing Center. And I will present like two things. First, I will present some work we have done like a month ago at Lugano in the EUROHACK. It was on porting a part of ALYA to GPU, so using OpenACC. And then I will talk about KNL, and we will use at least the same example in both cases, and at the end I will compare everything together. So first, the presentation for the GPU part. Well, we have a CFD code. This is the kind of problems we do. I'm a mechanical engineer, so I work with finite elements for CFD. I guess that not many of you are aware of what are finite elements, something similar to finite volumes or finite difference. You partition the space that you want to simulate into cells, and well, then you generate a matrix there, or a right-hand side if it's an explicit method. And well, you assemble this matrix for each element into a big matrix for all of the problem, and then you solve the system with a linear solver. And you get your velocities and pressures. Well, the first example that we are going to study is the flow around a sphere. This is a semi-implicit problem. This is related to a time discretization. The velocity is treated explicitly, and the pressure is treated implicitly because it's an incompressible flow and there is no other way to treat the pressure in that case. So the two most consuming tasks are the generation of the right-hand side for the velocity, and this changes at each time step. You need to calculate a right-hand side vector, and the solving of the linear system for the pressure, because we are in an implicit problem. So, well, we already had some stuff done for the solvers in GPU. I will talk about that later very briefly. I wanted to do the part of generating this right-hand side on GPUs using OpenACC, because it would be easier for all of the people that want to code similar things, and it would be easier for scientists than using CUDA. So, well, in a finite element code, in the generation of the matrix or this right-hand side, you have like three basic steps. Suppose your unknown is the velocity, then you have your unknown in all of the nodes of the mesh, and you pass this to the unknowns at each element. You deal with one element at a time normally in a finite element code. So you get the velocity, and you have the velocity on all of the mesh, and then you go for one element, you get the velocities at each of its vertices. This is called the gather. Then you calculate the matrix there, or the right-hand side if it's an explicit problem. And finally, you have to assemble this into a global matrix or global right-hand side. And in order to take advantage of vectorization and also to take advantage of the GPUs, we will work with groups of elements at a time, not just one element each time, but we will assemble a group of elements each time. And so we have this vector size that appears here, that is how many elements you will treat together. And this will help the vectorization, because it will do like perhaps 4 or 16 or 32 elements at a time. So we first modified our code that typically in a finite element code, you have, for example, for the right-hand side, it is of size NDime, that is the dimension of the problem, 2D or 3D, and P node, that is the number of nodes that an element has. If it's a triangle, it has 3 nodes. We added this vector size that might be, I don't know, 4, 8, 16. You set this at compilation time. And then in order to make this suitable both for GPUs and CPUs and KNLs, we put this if-def. In the case for OpenACC, we put this as evect, and we add this additional do. You have to make this do explicit in the case of OpenACC. In the case of the CPU, we just use here 1 to vector size, and so it's very easy for the compiler to vectorize it. So, well, we did this work at this EUROHACK. This was in Switzerland. We used the P-stained machine. And so we first had a benchmark by running only with the CPU. We ran in 12 cores, that is 1 node, or 24 cores. I believe we also ran 48 cores. And these are the times we had. This is what with the Intel compiler, well, the mesh was 2 million elements. And then we passed this, we added the OpenACC directives, and we ran it with the GPUs. And here we see the results for different vector sizes. And this vector size that I talked about before in the case of the GPU is really very big. The optimal turned out to be 128K, that is 131,000. We had never expected this at the beginning. We had thought about 4,000, but well, this turned out to be the best time, and we got 1.64, nearly 2 times decrease in CPU time. So then we did a bit of profiling, and I will just zoom at these 3 numbers. Here all I want to say is that these 3 typical operations that you have in the generation of the matrix or right-hand side in a finite element code. The first one is the gather, where you pass the values from all of the unknowns in the problem to each element, and that takes only 1% of the time, so it's very little time. Then you have the actual calculation of this right-hand side or matrix, and this is the important time. Here is 98% of the time. And finally, you have the scatter. And the scatter, in this case, it's very small. It's just 1%. But in this case, we're dealing with an explicit problem, as I said before. And therefore, it's not a very big amount of data that you have to scatter. It would be much more data if you had a matrix. We'll go to this later. So, a summary of the things done in order to enable ALYA to run in GPUs, at least the right-hand side assembly. It was quite easy after all I had heard and all the terrible things it seemed. We just had to add a ACC parallel loop GAN vector default in this do over the do that I had shown before. And then we had to add some copy in and copy out and create in the logical points to do it, but that, for me that I knew the code, it was quite easy to know where I had to copy in, copy out. We also added, in the case of things that were in the modules, we tried to avoid as much as possible things in the module, but well, those things we dealt with pragma enter data and exit data. And we did some optimizations. This was not done by me, but basically to reduce the registers. This I still don't understand totally. But well, a bit reduced the number of lines, and well, we got some further improvements with that. So, what did we accomplish in this EUROHACK? For this subroutine, that it's just one subroutine, but it takes typically 60% of the time of the whole simulation. We managed to pass this subroutine to OpenACC so that we could use the GPUs. We obtained a speedup of around 2.1 against one P-stained node only using the CPUs. And well, and the most important thing is that it didn't turn out to be very complicated. In 1 week, I could more or less understand most that we did. Well, so what do we have to do? Well, before going to this hackathon, I had prepared a special subroutine from the one we typically use. And the main thing is that I removed all of the if. We have different options of numerical treatment or whatever. And so I eliminated all of the ifs. Then in finite elements, you can use different elements, tetrahedra, hexahedra, pyramids, and whatever. And I just left one element that are tetrahedras. This, we would like to generalize it. And as I have said before, we have dealt with an explicit case. I would also like to see what happens in an implicit case. Well, we have done this for incompressible Navier-Stokes, but well, our code also deals with temperature equations, solids, and well, supposedly we can change this to the other parts of the code. Well, was it worth it? Was the last question here. Yes, I didn't have any experience of OpenACC 2 months ago, 1 month before going to this EUROHACK. Well, I didn't do everything myself, but I understood nearly everything that has been done, and I believe I could do it in some other problem. Well, it was very nice there. Lugano is spectacular. So I will now join this with what we have been doing on KNLs. The photograph or the picture behind is one of the examples. Is the flow within the city of Barcelona. This is for contaminant dispersion. And well, we are several people here in Barcelona Supercomputing Center. So in this case, we will deal with 2 cases. The first one is the same as in the previous example, the flow around a sphere. This is a semi-implicit time discretization, as I have already mentioned. The velocity is explicit, the pressure is implicit, but this matrix doesn't change with time. So the 2 main computational demanding times are assembling or generating this right-hand side for the velocity and solving the system for the pressure. Instead, for the flow in the city, we use a totally implicit formulation, and then we have to, at each time step, we need to generate a matrix for the velocity and the pressure and solve linear systems for both velocity and pressure. Well, I will start with the flow within the city. And we have run this on a machine we have there at Barcelona, provided by Intel. It's a 7210 KNL, 64 cores. And then we played around with different options. We can do pure MPI or hybrid OpenMP MPI. And so we tested from 64 MPI up to 256 MPI and with different number of threads. Actually, we tested even less number of MPI and more threads, but that was terribly slow. I haven't shown it here. And so what we get is that if you put 64 MPI and 1 thread, that is no use of hyperthreading, we get a time of 6.23 seconds, and you get the best time using pure MPI, just 1 thread, 4.37 seconds. If you put a blend of MPI and OpenMP, it goes lower than the pure MPI, at least for our problem. What was interesting to me is that we see that hyperthreading reduces the CPU time by 30%. But I know that in lots of supercomputers, hyperthreading is not enabled. Actually, in Barcelona, we have 2 KNL machines, and this is kind of the experimental one. But in the production one, hyperthreading is not enabled. And then, well, we see that, as I have said, MPI is faster than OpenMP plus MPI. And I have added this small comment. We have used flat. Before coming here, I didn't know which was the alternative to flat, but now I know we have cache and flat. The guy that set up this thing that was more computationally oriented than me, he decided to use flat. Well, and then for this same case, I will analyze the effect of the vector size. This vector size is the thing that I explained at the beginning, how many elements at a time we give to calculate. It can be just 1. This would be what happens normally in any finite element code. Or here we tested different numbers up to 128. And we see that we get the best results between 16 or 32 vector size. This is on KNL. In the normal CPU, we have observed that we get the best numbers with 4 or 8 vector size. Well, we can see that in this example, the vectorization nearly reduces the time. Well, nearly, no. It reduces the time by approximately twice. So, well, it's a very good thing to use. Well, we have results with 64 MPI, that is no hyperthreading, and 256 MPI, that was where we had the better time in the previous example, that is with hyperthreading. Now we can compare the times with Mare Nostrum 4. This is a new machine in Barcelona. It's the Skylake, if I'm not wrong. It's the Intel 8160. It has 48 cores. And this same thing in the Mare Nostrum machine that is very, very new takes 1.78 seconds. So the best time with KNL that we got without hyperthreading, we compare without hyperthreading because hyperthreading is not allowed in Mare Nostrum 4. So KNL is 3 times slower. Now I go to the other example, the sphere case. And in this case, I won't repeat the thing about hybrid MPI or hybrid OpenMP MPI. I will just work with no hyperthreading because I want to compare with Mare Nostrum. And so I will just test the effect of the vector size. Again, we see that we have the best numbers for 16, actually 32 in this case. And what we see is that in this case it is 6 times faster than if you do with vector size 1, that is what would happen in a normal finite element code. Or at least as we had our for a long time. I understand that most finite element codes work that way. So now we compare this case with Mare Nostrum, one Mare Nostrum node, and we have 0.83 seconds. That is, it is 1.4 times slower. So there is a big difference between this case, the sphere case, and the city. Well, it's treated different. One is semi-explicit, the other one is implicit. So we'll try to explain which are the differences. Moreover, in this case, this explicit case, or explicit for the velocity, I have used an optimized version of the subroutine that creates the right-hand side. That is the one that I developed for the GPU workshop at Lugano. That, as I have said before, there I eliminated lots of if and whatever. But I can still run with the older version without those optimization, and in that case I see it is 1.9 times slower. So, well, part of the difference is explained, but not all of it. It seems that, well, having a more optimized code is better. The improvement with KNL is bigger than the improvement with a normal CPU. And now, in order to further understand, we partition the times of the generation of the matrix in the city case, and there are different parts. I have actually talked before about the gather. This is where you send the values from the global nodes to the element nodes. But, well, the most two computational demanding parts are actually calculating the element matrix and doing the scatter, sending that matrix from that is at the element level to the global level. And we see that the element matrix, more or less, the time is twice, but instead, doing the scatter, the time is 5 times bigger in the KNL. This is for you pass from a small matrix to a sparse matrix, and well, this is there is a lot of indirect addressing, I believe you would say. And this is known to be complicated for GPUs, I also understand for KNL. So once I saw this, I just removed this part. I will not get the correct physical result, but just to look at the times. And now I get that it is 2.06 times lower. So I have identified the differences between the two cases. The matrix scatter is very slow in KNL, and this will be a problem in all implicit problems. In the case you have an explicit problem, what you scatter is much less, it's just a vector, and as I showed before, it's not a problem. And well, the optimized version works better or the advantage is greater in the KNL. So I tried to do an economic and energetic comparison between all of the different machines I had been using lately. I had Mare Nostrum, that one node has 48 cores. It's Intel Xeon 8160. KNL, that is one node with 64 cores, Xeon Phi 7120. Then Pisane, that I have compared just the CPU. And since it was, each node has 12 cores, to make the comparison a bit fairer, I put 4 nodes, so that is the same number of cores as Mare Nostrum. And Pisane, including not only the CPU cores, but 4 GPUs. The GPUs are NVIDIA K20X. So I got these numbers from around the web. And there you have the number of cores, the maximum energy it consumes, the prices of the different machines and when they were launched, and well, theoretical peak performance and bandwidth. Well, the prices are very different. The new Mare Nostrum is much more expensive. Each chip is you have 2 chips in a node, and in total is $9,000. The other are more or less similar. This is where I got the data from. And so here, for the case of Pisane, where I am using 4 nodes, I multiplied the values before by 4. And then I added these final 2 lines where I multiplied the CPU time by the watt, the max watt. This is one part that I would like to improve, because I'm not sure if I'm using the max watt, but I believe that somebody did the same here. I talked with the support guys at Barcelona, and they told me that they could measure the energy, but they had to physically connect with a USB to the node, and well, that will be cumbersome. They said that we could do it. And so here I have CPU time times the maximum watt. For example, 1.19 times 215, you get 256. This would be representative of the energy that you consume. And then CPU time times the price of the chip. You would also need to include the disk and whatever, but well, this is just the first approach. And what you see here is that if you go to price, KNL is spectacular. It's much way better than anything or any of the other machines. In the case of the CPU plus GPU, you have this thing that kind of complicated me, because you have to add the price of the 2 things. And so I also put the case of if only the price of the GPU were taken into account. That would mean that you can port all of your code to the GPU, and you had another machine with a...
Maybe a remark. So as far as understood, your GPU implementation concerns only 60% of the execution time, right?
Yeah. I'm looking at that execution time.
Exactly, but so the parallelization of the GPU cannot be compared to the parallelization that you have on the CPU, right?
Sorry?
The amount of parallelism you are able to express on the GPU is much less than the one that you can express to the CPU, because all the code is parallelized on the CPU, right?
Yeah, but actually we also have the solvers for the GPU. I will talk about that later. And actually, if I were in a case of a compressible flow running fully explicit, then I would have no solver. So just looking at the assembly is interesting anyway. I prefer not to look at the solver because, well, we can do things with the solver. There are lots of solvers we could use, solvers that are prepared for GPU. And so for the moment, I just consider in the assembly part, but this is not just a theoretical thinking. It's something that, well, if we were in a compressible flow, we would just be doing assembly. So, well, regarding to the price of the chip, KNL is the best. And if you could do CPU plus GPU and use a very cheap CPU, GPU would also be competitive. If you go to energy, both, well, the Intel approach is the best. Either the new Mare Nostrum or the KNL use more or less the same energy, and it is quite low. It is interesting to compare Peace-Dane, just CPU, with Mare Nostrum 4. These are two Intel machines, and this for me just means that Intel is doing a good job, because in a couple of years, between 2014 and 2017, it has reduced the energy 3 times. This is just CPU. Well, here I have the same data, but more simplified. Well, just what I had said before, KNL is best option price-wise and very competitive energy-wise. We are comparing using the maximum energy consumption of the chip, and I don't know if it is the same in the percentage that they are actually using is the same in all machines. We would have to actually measure. Mare Nostrum is the best energy-wise, and here, well, I have to take into account, people always say that the GPUs are very efficient. I haven't seen this, but perhaps it is because the GPU that I tested is quite old. It's the oldest of all of the chips I have tested. Perhaps things would change with a newer CPU. Well, here about the conclusions about the GPU. If the CPU was cheaper, perhaps in total it could be competitive. In energy, I have already said that it's not competitive, at least from what I have seen. That still is to be improved. Well, and I use these two measures that I found interesting, that are price or energy, price of the chip or energy consumed, but then in real life, you depend more on which is the offer or demand in price, and perhaps I understand that it is quite easier to get access to GPU machines, and so perhaps in real life the price or the energy consumption is not that important. I have worked everything with double precision, but perhaps some of the things could be done in single precision. I understand there GPUs would have much better advantage. We could also, well, test newer GPUs, and we think that we could do co-execution, that is generating the matrix part in the GPU and part in the GPU. What about the solvers? That is the part I haven't mentioned. I won't put times here, but Mare Nostrum was the best option. It was much faster than the other options in these cases. We have not explored any iterative solvers that are particularly suited for KNL. I understand that the Intel Math Kernel Library, MKL, has at least basic solvers for basic iterative solvers that should be well suited for KNLs. Regarding CPUs, we have somebody has been working at BSC, and he implemented a library of iterative solvers in CUDA, and he obtained 7 times speed up. Unfortunately, for the moment, due to compilation issues, I haven't been able to test it, but supposedly it should be very easy or quite easy. And then I am planning to install a library called PS Blast plus an preconditioners called MLD2P4 that is developed by Salvatore Filippone, that is part of EUROHACK, and this has support for GPUs, and I guess that perhaps for KNL. Well, thanks.